Hello and welcome to Calculus in the PM. In case you're just joining us, my name is Mr. Shindelka. I will be your host. This is part 2 of the chain rule, 4.1. November 3rd, the year is 2016. Okay. Let's take a look here, guys. We can use the chain rule with sine functions, cosine functions, etc. What do you have to remember, though? The derivative of the sine function, I'll just put this off to the side here. If I said like this, d by dx of the sine function. Now this is without saying that y equals the sine of x, dy by dx is equal to, and you tell me, derivative of sine? Cosine. Do you understand how this notation works here? I hope you do. So then, what's the derivative of the cosine function?
Negative sine.
Negative sine. Okay. Of x. And then there's the tangent ones, secant squared x, etc. Okay. But we're sticking to sines and cosines for these examples. Okay? Actually, they're all sines here. Okay. A. We've got a function inside a function. Now, I blackened this to what's the inside function? I tried to make it obvious, right? 25x is inside the sine function. So this is the innards. The sine function is the outer function. Does that make some sense to us? I hope it does. So I'm going to say A. F prime of x is equal to the derivative of the outside function, leave the inside alone. What's the outside function? It's sine, right? So the derivative of that is cosine of whatever, we're going to leave it alone, times the derivative of the inside function. What's the derivative of the inside function? 25. Now I'm going to separate that. By the way, this was leave it alone, right? 25x. That didn't change. Okay? We digging that? Okay, that's f prime of x. Anyone? I did that real fast. Now, maybe B or C, I guess I'm doing. What would you consider the outside function? What would you consider the inside function? As long as you can identify inside, outside, you can usually do the chain rule pretty easy. I'm going to ask someone from the right-hand side, my right-hand side of the room. Everyone's looking down except Sarah and Ryan. Ryan, what's the inner function on C? That's actually 7, and then that's a theta there. It's kind of fuzzy on the print of the. That's a theta though. Yeah, 7 theta is the inside function. Correct. That's the inside function. 3 sine is the outside function. Makes sense? So I'm going to just do this so you get the knack. 3 sine of something. What's that something? 7 theta. Now, would it be correct to say dy by dx in this case? What's the variable you're doing it with?
Y, so y prime?
What, y prime, but let's use the dy by d theta. Just because, you know, if it was a t, dy by dt, that kind of thing. Just to get you used to that. We're doing the derivative of the y function with respect to the variable theta. Okay? Now, I don't care that this is 7 theta inside here. If this was 3 sine of x, what would the derivative be? 3 cosine of x. Now, we've got the, leave the inside though as is though. So it's 3 cosine. It doesn't matter what's inside. That first step will look like that, except for the green, right? Then you do the derivative of the next thing. So 7 in this case, right? Now, I'm going to show it as a separate step. But do you guys understand your notations? Now, you don't typically do this. I guess you could put the bracket here. But do you guys understand that 7 is multiplied by the cosine function, right? Like, it's not inside the cosine function. However, this 7 theta here, you cannot divide out. Remember how you guys had problems with the limits, and I was like, shame on you, you know. You can't divide or multiply directly into here. You have to use identities, and I'm not going to make you use identities for the most part. Okay? So that 7 theta there is stuck. But what can you do? A slight bit of simplification, not a lot, but
3 times 7.
yeah, 21. Okay. Now, if it isn't confusing, I often don't write the bracket there, just cos of 7 theta, and that's often how you see it, right? Here I'm doing the bracket in the blue here and stuff to really emphasize inside outside. Okay? That's why I've added brackets there. It's not necessary, but I think you'd find it easier to just do the rules properly. Questions? Because the questions, they don't get too bad, actually. Can I get you guys to try E real quickly, and then we'll compare? There's a little bit more to E, but there's not a lot more. Essentially the same problem with the derivative inside is a little extra. You do E, we'll see. But then F, there's a little extra to F and G that we're going to do. But if you get those ones, you should be able to do E. And your second step, you can simplify by multiplying 2 with E. Step back, I suck. Can't read that. 2x to the 4. Hopefully you got E down. I haven't done it yet, but the outside function, the derivative of 9 sine of something is 9 cos of that thing. Don't change it. And then the derivative of the inside function is 8x cubed. The only thing you can do now is just multiply 8 and 9. 72x cubed cosine of, now this one I'm going to use bracket anyways. So it's not ambiguous. You all agree? Okay. Now, notation here before we do F. We have to understand. When you see something like sine 4, or when you see sine squared then x, what does that mean? Sine squared x. So if I said sine squared x plus cos squared x equals 1, what does sine squared x actually mean? Like,
it's like if there's a bracket.
This is the same as, it's in a bracket, this, right? It's a neater, tidier way to write it. But for calculus, at least when you're first starting these chain rule questions, I will suggest that you rewrite it like that with the square, only because then you can see all the outside function in this case is squared. Then the inside function is sine of x. Do you follow me on that? This next example has 3 functions. Ah! Yeah, it does. Truly does. Okay. So, F. I'm not going to do calculus first. I'm just going to write it. F of x equals my outside function. What's the outside function in this case? To the 4. Does that make sense? Okay. So I'm going to write a big bracket here, 4. And that's because of this little doohickey there, right? Sine to the 4, 3x. Then the sine function is the next function, the sine of. Now, I don't need that bracket. I'm only doing that to show that this 4x, or 3x is inside it. You guys follow me on that? Now, composite functions are like ogres, right? Because ogres are like onions, right? Because onions have layers. You guys know this. And these problems stink. You got to work out in the outside layer, that's the red. To the middle layer, that's the blue. To the inside layer, green, right? See? It's like an ogre. F prime of x is equal to, do the outside function. Don't change anything else. So 4 times whatever cubed. Does that make sense? Okay, now I'm going to fill in that something else. Actually, I'm going to make a little more space. Okay, we've taken care of the outermost function, right? Now the middler, that's the sine function. We don't have anything in red to write down anymore, right? We've taken care of the outside function. So the derivative of the sine function is the cosine function. So times the cosine function with the inside left alone. If you write it right beside it, it means multiplied. If it makes you feel better, go ahead, put brackets on here too, that's fine. Then you do the derivative of the inside green function in this case, 3. Is there much you can do here? I'm not going to ask you to use identities unless it's a really obvious identity like cos squared of x plus sine squared of x. So, no, there's nothing really obvious, is there? No. So, it's just 12, number-wise. So do that kind of thing, always 12, sine of 3x. What's the conventional way to write sine of 3x and then cubed? It's sine cubed 3x, isn't it? Do you guys follow what I'm saying? Because the answer book will say this. Sine cubed of 3x cos of 3x. So that's just a notation thing, right? Now G is essentially the same problem that we just did. I'll show you a nifty way to do that. You could use the quotient rule. I'll show you one way not to use the quotient rule. I mentioned it yesterday and I didn't show it to you. How could you rewrite this so that you don't have to use the quotient rule with the negative exponents? How could you rewrite that?
Sine 10x to the negative half.
Negative half. Good. So I'm going to rewrite that before I do any calculus. Is that an f of x function? Oh, it's a y equals. Okay. Y equals, like you said, negative half. Don't need that much curve on there. And then sine, was it? Yeah. Sine of, and then 10x. Now I'm going to drop those brackets around the 10x that I was often putting there because I think you guys are getting that part, right? The 10x is inside the sine, which is inside the square root, which happens to be on the bottom. That's why I made it negative. If you want to keep it on the bottom, go ahead and you'd have 1 over the sine of 10x to the power positive half. And you could use the quotient rule. That's an option. I just thought I'd show you. Sometimes it's simpler to do this way. dy by dx or y prime, I don't care which way you want to say it. Use an appropriate notation though. And then we just say negative 1/2. Negative 1/2 subtracting 1 is negative 3/2. Inside left the same. Then I am done with the square root portion of this, right? I now do the derivative of the middle inside, I guess, the blue sine. The derivative of the sine function, as we know, cos. Leave the inside alone, 10x. Then I do the derivative of, it's going to make me feel better, so I'm going to do this. 10x, it's just 10. Then you say, I'd never see this in the back of the textbook, probably not. But if I ask you only show the first step, that's what you'd show, right? Don't go any further. But sometimes you are asked to simplify without using, and I usually say simplify, but do not use, oh, marks, I don't want those up now. I don't use any trig functions, right? So, number-wise, I'm thinking 10 times -1/2, -5, correct? Numerator. So, -5. What else is going to remain on the top? The cosine of 10x, right? The -3/2 gets taken to the bottom. And as soon as you see -3/2, okay, bottom, so now it becomes 3/2. And square root, that takes care of the half part. What about the 3?
So now it's
Cubed, yeah. Now, you could put the cube inside, and it'd be sine cubed 10x under a square root, or you could put the cube on the outside. I'm going to put it on the inside. That's just a choice. I usually keep it on the outside, actually. But this time, I use the old school square root notation. So, if you wanted to, as I mentioned, you could take this here and put it there, outside. And that's just nifty too, right? Same expression. All good? I've been going fast, but I think you guys are pretty smart, so. But if you have questions, you ask me. I'm going fast because I want to give you a little bit of work time for these too. No question. Okay, we will flip the page. And this is it then, this page, and then I got some questions for you. Here's one from page 153, number 6 from the assignment. Find the derivative for this equation. Now, before you do any calculus, I would suggest you rewrite this. Now the 5 cotangent part, just leave as 5 cotangent, right? It's the inners. What's a better way to rewrite that so you don't have to involve the quotient rule? 2 over x is x to the -1. Okay, 2x to the -1. You can use the quotient rule, don't get me wrong, I'm fine with that. If it's a simple expression like 7 over x squared or something like that, I tend to go x to the -2. If it's something like x plus 2 on the bottom though, I keep it there and use the quotient rule. Okay, now we can do calculus. Find the derivative. You have an idea. You guys tell me. Remember the co-identities? They always have a what sign on their positive? Negative. Okay. So this is going to be -5. And the cotangent itself, you guys might not be as familiar. Tangent is secant squared of x, the derivative. Cotangent is negative cosecant squared. Okay. So I've got the negative sign already. Squared of, well, that remains the same. And then we do the inside. So the 2 over x or the 2x to the -1. I'm going to put it as 2 over x because that's the way it originally appeared. This is an equivalent expression. I'm just doing that because that's likely what the textbook would have in the back of the book. But I'm thinking of it this way, 2x to the minus 1, because it makes it easier to do my derivative without writing it out. Because now, the derivative of the inside is negative 2. Negative 2x to the negative 2. Now, I'm going to just jot that down over here. And that's good. This is what I'm thinking, but can you do this in one step? If you want to, do it. If not, don't. Write that down where I have the arrow. If not, if you could do this, what could you write that as a fraction?
Negative 2x over 6.
Almost what you said. Negative 2 over x squared. I think you said negative 2x, but does that make sense? Okay, that's where that came from, though. That's why I have that arrow. That's what I would think in my head. And actually, when I was your age, I would have actually written it out fully, but I know some of you guys are smarter than I was, and so I wouldn't doubt that some of you would just pull that off in one step. Now, the only thing left to do there is negative 5 and negative 2 is 10 over x squared, etc. Okay, I'm going to leave that one there, though. Okay, 10 over x squared, and then cosecant 2 over x. Are we good with that? Huh? Yeah, maybe. Finding slope. This is an AB question. This one's a little more involved. Find the slope of the line, okay, derivative, tangent to the curve, y equals sine of x to the 5th power, at the point where x equals pi thirds. And then show the slope for b, blah, blah, blah. So, A. The first thing you're going to do is a derivative, right? Even though it says sine of, when I see this, I'm going to think this is really, now, whether you literally rewrite this or not, that's up to you. But I think you should think of this as to the 5th power with the sine of the function inside. If you're just joining us, this is Calculus in the PM. Welcome back. We're just continuing on with example 7. Just in case somebody's watching the recording halfway through. Anyways. Derivative. We need it. So I guess this is A. dy by dx. 5. Leave the inside alone. Then the derivative of the sine function, cosine. And that's that, right? If there was more to simplify, I wouldn't, because I've got to evaluate anyways, and it looks fairly simple to evaluate. Do you guys memorize these things? I don't, really. Most times I have trig functions and stuff like this. This is what I need to memorize. 2 triangles. 1 radical 2 for the 45 degree or pi quarters, right? This is pi thirds. Pi sixths is the smallest end of 30 degrees. But pi thirds is equivalent to 60 degrees, right? What are the sides of this triangle? What's the shortest? Uh-oh. Okay. 1, 2 radical 3. You just say it like that, and then you can think it through. Like 1 radical 2 for the 45 degree one, right? And you just kind of draw a 45, and you know 1 and 1 are the same side. 1, 2 radical 3. Well, the shortest side is 1. 2 is the longest side. And I know radical 3 is less than 2 because square root of 3 would be less than 2. Square root of 4 is 2, right? Radical 3. You should have this memorized, right? And you guys, this is not news to you, right? This one? No? If you don't know what I'm talking about, come talk to me later. Okay, because the sine function, SOHCAHTOA, sometimes SOHCAHTOOMI, whatever you guys, it's a gimmick, but it helps you memorize it. Root 3 over 2, opposite over hypotenuse, right? Okay, root 3 over 2. So I've got 5 times root 3 over 2 to the power of 4, and then the cosine. adjacent over hypotenuse. So I'm looking here, a review. Here's pi thirds. What's beside it? 1, and then the hypotenuse is 2, half. Oh. Now there's a slight bit of arithmetic, nothing crazy. 5's fine. What is root 3 to the power of 4? Well, what's root 3 times root 3? So there's the square. And then you'll get 3 times 3, it's 9. You can do this without a calculator, right? So I'm going to write it out a couple steps here then. 5 times 9 out of 2 times 2 times 2 times 2, 16. Times half. So, I hope you guys can do this arithmetic. 45 out of 32. Improper fractions are just cherry. Keep. Okay? Are we good with that? Yeah, I don't. Mixed numbers are for elementary school. Just kidding. But in grade 8, weren't you told to always give your answer as a mixed number and stuff? Yeah. You don't need to, actually. It's more useful, 45 out of 32, if you had to do more arithmetic, right? Okay, what's B asking? Show that the slope of every tangent line to the curve, 1 over 1 minus 2x all cubed, is positive. How would we do that? Slope of a tangent, well, right away that tells you you need? Do the derivative. Okay? Then you can show that it's positive. It must involve an even power then. Not an evil power, an even power. Because then things would come out to be positive. And even. Where do we begin with B then? Times, yeah, or the derivative here. I'm going to put B over here. You know what? I'm going to rewrite this one. And I'm not going to color code it. I'm just going to go with 1 minus 2x to the negative 3. I think that's easier. Or is it? Yeah, I'm going to try that. Okay? Then the derivative is, I'll use y prime notation so you see something different. Outside, negative 3. Subtract, there you got negative 4. Inside remains the same. Here's where people sometimes get messed up then. The derivative of 1 minus 2x is negative 2. Sometimes drop the sign. So to simplify y prime, the derivative, I've got negative 3 and negative 2, so 6, positive. On the bottom, I've got 1 minus 2x to the 4. Can you dream up any way you could get, within the real numbers, any way you could get a negative out of that expression? The denominator's never negative since you have an even power, right? My goodness. I'm going to stop the record. There we are.